All right, so let's continue here. What we're going to do here is we're going to look at an example where we take an ice or ice cube, right, at negative 25 degrees Celsius. And we're going to, as I was saying, increase its temperature to let's say, 130 degrees. Okay. So let's say we're going to start with initial temperature of negative 25 degrees, and we're going to go to a final temperature of the 130 degrees. Now, what we learned that between those two temperatures, negative 25 and 130, we're going to have two phase changes, because what I have here is ice cube going to melt, then water going to evaporate. That means what I need to do here is I need to take into account all of those phase changes plus all of those instances where the temperature is increasing because of the added energy. That means this diagram is a very useful diagram if you understand how to, let's say, approach this type of problem. And hopefully at this point, if you're able to follow along, this diagram going to really allow you to break it down into, let's say, several parts, and then start writing the equations that needed to achieve, let's say, some kind of final temperature. So let's start with that. So, all right, so first we are given some ice cube. So we have ice cube with mass M and temperature initial of negative 25 degrees Celsius. All right, so basically, if I put it in a diagram where the temperature is, you can see on a vertical axis, right? And the time on an x-axis, horizontal axis, then what I have here is at t equals 0. So this is basically at t equals 0. I am at negative 25 degrees Celsius. I'm at the temperature at t equals 0. Because everything, including, let's say, phase change or temperature increase, takes time. Nothing is instantaneous. So that means all the graphs going to be as a function of time. Now, what I need to do here is, since remember, my goal here is to go to all the way to this final temperature of 130. That means I need to increase the temperature of the ice cube. All right. That means what I have here is I have a stage, during this process where I add energy, and that energy will go into increasing the temperature of the ice cube, because ice cube, let's say here is when you have ice, ice is at negative 25 degrees Celsius. If I pump energy into this system, right, where I have an ice cube is my system basically, any added energy will go into increasing the temperature of this ice cube. Okay, so let's say I can solve this, stage, let's call this stage 1, by calculating the energy Q1, which will be then mass of the ice cube times specific heat of ice, then times change in temperature. All right, so what will be my change in temperature in this case? So let's say mass of the ice cube, for example, I don't know, let's say 10 grams, nothing wrong with that. So let's say we don't have to worry about converting to kilogram for now, because I'm not going to be calculating anything in this particular example. So let's say it's 10 grams. Now what I have here is, let's say I have 10 grams water, specific heat of water, remember, 10 grams of ice cube. Remember, there was a table with specific heat of, ice, right, ice cube or ice. Now this is the delta T. So what will be the delta T? By how much the temperature of ice cube can increase? Well, remember, if you start with negative 25, that means the highest it can go here is 0 degrees. So 0 minus, final minus initial, right? So 0 minus negative 25 degrees Celsius. So that's kind of what I have. This is my T final minus T initial for the stage 1. And in the graph, I have then, this is stage 1. I start with, here at position, let's call that A, right? And where this position A represents the position of the temperature of my system, and that's a negative 25 degrees. And then what I will go here is this Q1 will be energy added to the ice cube system, and it will increase its temperature all the way to this point B, which is the 0 degrees Celsius. Okay, so that means we arrive to that, point B. And you can see, right, it's a linear increase in the you know, let's say temperature as a function of time. That means, you know, as you add energy, the temperature increases linearly like that. All right, so now point B, then we arrived here. So this is, we arrived as, you know, let's say ice at 0 degrees Celsius. So point B is basically what we have here is ice at 0 degrees Celsius. Okay. Remember, where point A here, I had ice. So point A here is, right, ice at negative 25 degrees Celsius. Then what do I do? Well, in order to continue, right, let's say the process of increasing the temperature, I have to right now, you know, before I can change any temperature, I mean, before I can increase any temperature, right, I need to first melt the ice. That means what we have here is there is a time period where all the added energy will go into increasing, will go into melting the ice rather than increasing the temperature. Because what I have, you can see right here, this is point B, this is point C. See, this stage, the temperature doesn't change because this stage is when ice melts to liquid water at 0 degrees Celsius. That means this is, you know, going from point B to point C, you still have the same temperature, but what we have here is ice basically melts. Okay. Now, what is the equation for that second stage? Well, for that second stage, equation for the Q will be then M of ice times LF, right? Heat of fusion. Why? Because I am changing phase. Is it positive or is it negative? Well, remember, you're melting, so it is positive. Remember, here you're also going to get a positive quantity, right? Because 0 minus 25 gives you 0 plus 25. That means this is for the stage 2, where you go basically from B to C. All right, so now, when we arrive to point C, then what I have here is, so ice melts, and point C here is then I have water, so liquid water, right, at 0 degrees Celsius. That means all my ice melts, and I have a, you know, all that water, right, you know, that, you know, melted ice, now it's water, right, sitting there at 0 degrees Celsius. Is water mass different from the ice mass? No, it's not. That means if I'm given mass of ice as 10 grams, that means my mass of water is also 10 grams because it's just basically same amount of, you know, substance, right? 10 grams ice will melt into 10 grams of water. All right, so now I get, you know, basically to this point C where I have, you know, water, 10 grams of water, right? Now sitting at 0 degrees Celsius. In order for me to continue, I need to then continue pumping heat. If I add more heat, then the temperature will increase. That means, let's, you know, remember this is stage 1, this is stage 2. Now I have stage 3, where any added energy will go into increasing water, because water at 0 degrees Celsius, any energy added to that will start increasing temperature. It's still going to be water, but it's going to be water at 10 degrees, 20 degrees, 30 degrees, 40 degrees, all the way to 100 degrees. That means going from C to D, I have water, okay? But I can change the temperature of water. And remember, there are 2 equations, right? One for changing temperature, one for changing phase. And here I'm changing temperature of water that doesn't have any phase change, going from C to D for stage 3. That means what I can do here, I can calculate the amount of energy that takes my, you know, 10 grams of water from point C to point D. That means for that stage 3. And then this will be mass of, you know, water and ice. Remember, same thing. So I can say mass of water, then specific heat, but now I have water. So then specific heat of water, then times delta T. All right. So again, what is my delta T? So this is, well, this is then from final 100 degrees Celsius minus initial, which is 0 degrees Celsius. That means this Q3 will give me how much energy I need to take 10 grams of water at 0 degrees Celsius and increases temperature to 10 grams of water at 100 degrees Celsius, because the water cannot go beyond the temperature. Okay, once I get to that temperature, the water, will no longer be able to change its temperature. Okay, that means any added energy into the system will go into changing the phase where liquid water vaporizes to steam at 100 degrees Celsius. That means at point D, so you can see right at point D, what I have here is I have water at 100 degrees Celsius. So I have water at 100 degrees Celsius. And what I end up with that, well, water at 100 degrees Celsius, any added energy will go and start vaporizing that 10 gram of water into 10 gram of steam. Okay, that means let's call this stage 4, and this is, let's say, Q4, right? And for this stage, what I have here is I have no change in temperature, because in this case, water cannot go beyond 100 degrees Celsius, but any added energy will go into changing phase. So this becomes mass of water times then heat of vaporization. Okay, and you can see, right, it takes a longer time and much more energy than just melting the ice. So it takes longer time to vaporize water than it takes to melt the ice, and more energy, obviously. All right, that means once I added enough energy to completely boil the 10 grams of water into 10 grams of steam, then at point E, what I have here is then I have steam, or we can, gas, right, at 100 degrees Celsius. That means what I have here is at that instant of time, right, at that instant of time, at point E, I have 100 degrees Celsius, right, temperature, but I have all that, 10 grams now in its gas form, okay? And this is amount of energy that requires to achieve that. Okay, what is the next? Well, now that I have all gas at 100 degrees Celsius, if I continue adding energy, so let's call this stage 5, then all that energy will go into increasing temperature of gas, because it's already all gas, so any energy will go into increasing. That means if I go from E to F, right, that basically will be, increasing, right? Increasing basically temperature. And for this stage, I have, let's say, Q5, and that will be mass of now steam, but it's same thing, right? Well, with the gas, right? Then times specific of, this water or steam, right? So it's probably better to put steam because we know it's water. So let's say steam, and then times the final temperature, let's say 130 minus initial of 100. And that basically will allow me to get to that 130 degrees. So you can see why I couldn't just basically use just one equation where I say, all right, so the Q is equals to MC times 130 minus negative 25. So trying to use this equation can always give you the wrong answer, because, going from negative 25 to 130 degrees, this particular substance, right, water, has two phase changes. See, this equation will work if I have maybe, like, say, I don't know, like, let's say copper or gold or something like that, because at negative 25, it's solid. At 130, it's solid. That means the entire time there is no phase change. I have no problem using this equation. Water, another case, has, phase change at 0 degrees Celsius, phase change at 100 degrees Celsius, and this equation cannot work. That means to calculate my Q net, I have to add Q1 plus Q2 plus Q3 plus Q4 and plus Q5. All right, where what I have here, hopefully I can fit everything here. So actually, let me then, since this is a video, you can rewind back. So let me do this, erase everything. So what I have is this. So Q net is equals to Q, stage 1. Q1 is this stage where I take mass 10 grams of ice times specific heat of ice and change the temperature from from negative 25 to 0. So 0 minus 25. Then I add energy for this stage 2. And over there I have a phase change, which is mass of ice times heat of fusion. Then this is the third stage where I have then water and specific of water, and I change the temperature from 0 to 100. So it becomes 100 minus 0 degrees Celsius, right? And then plus the fourth stage, where for fourth stage, I have mass of water times heat of vaporization. And then finally, I have the last stage where I have mass of steam times specific of steam, then 130 minus 100. That means after calculating all of this, then I can calculate amount of energy. So let's say I get 1.5 megajoules. That means that's the amount of energy required. You know, again, I'm just shooting this number. You can actually calculate it since I'm giving the mass and you have the specific heat. So you can actually calculate and see. So let's say approximately 1.5 megajoules. That means it's positive 1.5 megajoules. That means amount of energy added, positive means added, right? To melt and then, you know, evaporate 10 grams of ice cube into a gas at 130 degrees Celsius. Okay, so you can see that you have to kind of go through the stage. So this is increasing temperature of the ice cube. This is melting the ice cube. This is increasing temperature of water. This is evaporating the water. And then this is finally increasing temperature of the steam. Okay, so that means depending how many stages you have, right? So you have to take all of those into account. All right, so we should be able to then now do a few examples. So let's say Carlos takes a 10-kilogram bag of ice at negative 10 degrees Celsius from the freezer and puts it in the back of his truck. Unfortunately, he forgets about it and the ice melts. How much heat energy did it take to melt the ice completely? All right, so let's see what we have, how many stages. So temperature is a function of time. So we're given the mass, right? Mass of ice is 10 kilograms. And I'm given initial temperature of negative 10 degrees Celsius. All right, so let's see how many phases we have. All right, so there's one phase where, you know, he says he forgets and the ice melts. That means in order for ice to melt, it first has to go from negative 10 to 0. So let's say this is then stage 1. And then completely melt, right? That means we go from A to B to C. And then we are sitting here at C because it says, how much energy did it take for ice to melt completely? We don't care what happens afterwards. That means all I have here from A to B, B to C, that means I have 2 stages. That means my Q net represents Q1 plus Q2, just 2 stages. Q1 here is changing the temperature of ice cube. So this will be mass of ice, but if specific of ice times delta T, then Q2 here represents the stage where it melts. So becomes mass of ice times heat of fusion. All right, that means we have now only 2 stages because we don't go beyond, let's say, that point. All right, so let's calculate this. So 10 kilograms times specific heat of ice, remember, so that technically that's 2100, or you can write it as 2090, which is a little more accurate, but you know, 2100 is, you know, going to give you almost pretty much same thing. So joules, kilograms, Kelvin, and change in temperature, remember, so it's 0 minus 10 degrees Celsius or Kelvin, doesn't matter for us. Then plus 10 kilogram, so mass times heat of fusion, so 10 kilograms mass, and heat of fusion is 3.33 times 10 to the 5 joules per kilogram for the you know, LF. We calculate this, I get 3.5 millijoules. All right. So, and that's a lot of energy because that's 10 kilograms, right? I mean, remember I said 10 grams for the previous one? This is 10 kilograms. That's a lot of ice to melt. So you need a lot of energy just to, you know, increase temperature of the 10 kilogram of ice and then go ahead and melt it. Again, so here we stop at this point C because, you know, we are only looking at up to, you know, melting the ice completely. All right, so here's then kind of like the application of this type of, you know, problems. It is called calorimetry. And this calorimetry is basically a quantitative measurement of the heat transferred between the system or evolved reaction when we assume that the system here is isolated from the environment. Okay, that means, for example, if you have a, I don't know, hot coffee and you put a, let's say, ice cube in it, what happens here is because coffee and ice cube have different temperatures, right? Different temperatures, the energy will be, remember we talked about heat energy will go from hot to cold. coffee will lose energy, and ice cube will gain energy until they, remember, reach thermal equilibrium. That means they have, final temperature. So basically what we have two objects, right? So let's say we have, let's put like a liquid, right? So we have a liquid, because it could be coffee, it could be tea, I don't know. So let's say liquid, and let's say ice. So we have a liquid and ice. And what I have here is this. You need, let's say, liquid and certain mass of liquid, and then you have ice, and then let's say mass of ice. Okay, and remember, so if it's a liquid, then you have let's say specific heat for that, right? Specific heat for that and things like that. But the idea here is this. So you have two substances, and initially, let's say temperature of liquid is not equals to temperature of the let's say ice, right? So these are the initial temperatures, but final temperature of liquid will always be equal to the final temperature of ice, okay, because they will reach thermal equilibrium. And one thing we have here is this. If I am then looking at the system, that means this energy transfer between, so technically my, this cup, right, isolated, it has then, this ice cube, and it has like liquid, right? And the energy will be, total energy in the system will be constant, because how much energy is lost by the ice cube, or sorry, by the liquid, is gained exactly the same amount by the ice cube. That means what I have here is I can then look at two systems, because if I look at just the ice cube, it just gains energy. If I look at just, let's say, the liquid, it loses energy. But if I look at both of them together, right, then how much energy I have in the system before and after is the same, because all it does here is transfers from one object to another without losing, let's say, total amount of energy. So let's say what we have here is, to understand this, let's look at this another example. So you have an isolated system. Your total system consists of two subsystems, call it system 1 and system 2. And initially there you have T1, T2 that are not the same. They're different temperatures. And obviously then if there are different temperatures, there's going to be heat transfer. So here, by looking at this, you should be able to tell which one has a higher temperature. It has to be system 1, right? Because the arrow tells you that energy goes from system 1 to system 2. Q1 is how much energy, lost by the system 1. Q2 is how much energy gained by system 2. Okay, and one thing we have here is, because system 1 loses energy, Q1, I'll put it here. So Q1 here is negative, less than 0. And because system 2 gains energy, Q2 here is positive because it gains energy, right? And gained energy is always positive. Now, what we have here is that the Q2 is the energy transferred to system 2. Q1 is energy lost by system 1. And one thing we can do here is, if I'm calculating Q net, then what I get here is this. Q1 plus Q2 will always be 0, because Q1 represents how much lost by system 1. So let's say system 1 lost 100 joules, so negative 100. Q2 represents how much was gained by system 2. Well, system 1 lost 100 joules, well, system 2 gained 100 joules. And if you add them together, obviously you're going to get 0. And this will be always true for this type of isolated system. Your Q net will always be 0, okay? Because same amount of energy, added and lost by the, subsystem in your, let's say, in your entire system, let's say. All right, so let's look at an example here. An engineer wishes to determine the specific heat of a new metal alloy. 0.150 kilogram, which is about 150 grams sample of the alloy, is heated to 540 degrees Celsius. Okay. It is then quickly placed in 0.4 grams or 400 grams of water, 0.4 kilograms of water at 10 degrees Celsius, which is contained in a 0.2 kilogram aluminum calorimeter cup. The final temperature of the system is 30.5 degrees Celsius. Calculate the specific heat of the alloy. All right, so let's see what we have here. All right, so this is actually an experiment that we do in class whenever we have an actual physical lab. So here's my specimen. Okay, so it's some kind of metal alloy. So I'm given the mass of the, I'm going to put like here A for alloy. Okay, so A for alloy. And what I have here is, so initial temperature for alloy is 540 degrees Celsius. And then what I have here, I have a cup that is specifically designed, so it's a specific design where the cup is basically entirely isolated from environment. So you have, let's say, water, and the cup itself is aluminum, So then what I have here is this cup and water, in thermal equilibrium relative to one another, because let's say, so you can think like it's kind of like this, right? So this is the inner part of the cup, which is in equilibrium with water. So that means I can say that here's mass of water, and I'm given 0.400 kilogram. By the way, mass of alloy here is 0.150 kilogram. And then I'm given mass of the cup, let's say, put like CAL or calorimeter, right? And this is equals to 0.2 kilograms. And both of them, water and the cup, right, calorimeter cup, are in thermal equilibrium. That means T initial of water is equals to T initial of the calorimeter cup, and that's 10 degrees Celsius. Then what we do here, we take this specimen and we put it inside the cup and water, and then close this whole thing. Okay. That means you have 3 objects in your system, right? So that means I have, heat exchange between water, between the alloy, metal alloy, and between the calorimeter cup. Okay. And what we just learned, because they're isolated, this is my Q net. And that means if I add them all together, I will get 0. Okay. Now, what I have here is we're given the final temperature of everything. Okay, so we're told that final temperature of alloy, same as final temperature of water, same as final temperature of the calorimeter cup. That means we know that the temperature, it goes from 10 to 30 degrees Celsius. That means the entire time when water, let's say, gets energy, we can see, right, water, when, let's say, you put the alloy in the water, it goes from 10 to 30 degrees Celsius. Cup also 10 degrees Celsius. That means it also goes to 30 degrees Celsius. That means cup, the calorimeter cup, and water together gain energy. Well, where the specimen goes from 540 degrees Celsius to the final of 30.5 degrees Celsius. That means it decreases its temperature, which means it loses energy. Okay. That means what we have here is the energy will be gained by the water and the calorimeter cup, and energy will be lost by the metal alloy. But if we add all 3 together, we should get 0, because how much is lost by the alloy is gained by the water calorimeter cup combination. All right, so let's write this down. For the Q water is mass of water, specific heat of water, times delta T. Then plus, Q of alloy. Well, this is mass of alloy times specific heat of alloy times delta T. Then plus the calorimeter cup, mass of the calorimeter cup, specific, and we know it's aluminum. So we have the aluminum, specific heat from a table. So specific heat of that calorimeter cup, then times delta T. And this is 0. Remember, what I want to find is the C alloy, right? Specific heat of alloy. So basically that is my goal. I need to find this guy. That means all I do here is, just plug in everything and kind of calculate this, right? So mass of water is 0.400 kilogram times then specific heat of water, which is, 4190 or 4186 you can put, right? So joules per kilogram Celsius. And then delta T. Delta T here is final of 30.5 minus initial of 10. Then plus mass of, so this is basically this guy over here. Then let's do the second one. So mass of alloy, 0.150 kilograms times, Ca, again, that's something we don't have. But then temperature change, and this is 30.5 minus 540, right? And then this is plus, which basically this guy was for that. Then mass of the calorimeter cup, and that the cup was 0.200 kilogram, times specific heat of aluminum, and that's 900 joules per kilogram Celsius, and times temperature change. So we got 30.5 starting with the 10 degrees, and all that together gives us 0. All right, so if I calculate Q water, I would get then, let's say, 34,300 joules. If I calculate the QA, Q alloy, what I get here is negative 76.4 times Ca. Remember, Ca is unknown. Well, then if I calculate Q calorimeter, what I will get here is 3690 joules. And those three together added will give us 0. That means I have everything but this Ca, right? And we just, rearrange and solve for this Ca, and we should get 497 joules per kilogram, okay, degrees Celsius, let's say. So that's for the metal alloy, specific heat. Okay, that means what we do here is we add everything together. Added everything together is equals to 0, and then calculate those terms that we can calculate and isolate the one that, let's say, is unknown, and then just go ahead and calculate, the unknown quantity. All right. Here's, one more example. So this is going to be our last example. So 30 grams of copper pellets are removed from a 30 degrees Celsius oven and immediately dropped into 100 milliliter of water at 20 degrees Celsius in an insulated cup. What will the new water temperature be? All right. So here what we have is finding the final temperature. And generally this is kind of like the messiest of the calculations in this type of problems. Because one thing we're given here is the mass of our object 1, right, which is the copper, okay? And this is 30 grams. So 30 grams, remember, has to be, converted to, kilograms. So 0.030 kilogram. Remember, anything in gram divided by 1,000, that's your mass in kilogram. Then what I have here, because I know it's a copper, right? I know it's a copper. I know then the specific heat of copper, okay? And that will be 385 joules per kilogram Kelvin. Remember, kilogram Kelvin or kilogram Celsius, that's the same thing. And I know that I start with the initial temperature of the copper as 300 degrees Celsius. Okay. Now what I have here is things like this. So here's my container with water. This is not an isolated, let's say, this is not a calorimeter cup. So that means my only object in the system is the copper pellets and the water. Okay. But it's isolated from the environment. But this is a heat exchange between water and the copper pellets. Okay, so this is my object 1. And this is my object 2, which is water. And I'm given the water in terms of its 100 milliliters. What is 100 milliliters? Well, that's the volume, right? That's actually the volume of water. So 100 milliliters. All right. And I'm given that temperature of water initial is 20 degrees Celsius. Well, obviously, then I'm also technically have specific heat of water, which is 4190 joules per kilogram, degrees Celsius. So let's say, all right. So this is for water. And what I have here is this. Q net is equals to Q1 plus Q2, and it should be equal 0. Well, Q1 here is about, the energy lost by the copper, because, what I have here, you can imagine, right? If you put the hot, copper pellet into the, let's say the water in room temperature, then the temperature will be dropped for the copper pellet, temperature will be increased for the water, right? Then the heat will go from, let's say, copper into water. That's your Q, basically, Q net, right? So, or not the Q net, basically the direction of the heat exchange. That means the heat lost by the copper pellet will be heat gained by the water. All right, so let's see what we have. So Q1 is mass of copper, specific of copper, then times T final minus T initial for the copper. Then plus, then mass of water, that's for Q2, specific of water, then times T final minus T final water minus T initial water. And this is equals to 0. All right. So to do those calculations, I need mass of water, but I'm not given mass of water, I'm given volume. But here's the thing. So volume of water, let's say, remember, so it's 100 milliliters. So what I can do here is I need to convert this to, first of all, let's say cubic meters. So what I do here is, let's say, I can first convert it into where 1 milliliter is 10 to the negative 6 meters, and then convert to, oh, hold on. So that should be, what I need to do in terms of this, right? And then let's say if I do this, I should be able to convert that, right? So that means, milliliters goes away. So then I have 100 times 10 to the negative 6 cubic meters. Sorry, there you go. All right. And I can find the mass because I have an equation where mass of water will be equal to the density of water times volume of water. Density is 1,000 kilogram per cubic meters, and then times 100 times 10 to the negative 6 cubic meters. You can see cubic meters cancel out, and we're going to get the mass as, so 1,000 times 10 to the negative 6. So we get, 100, times 10 to the negative 3, or 0.100 kilograms. All right, so 100, 100 times 10 to the negative 3 kilogram, or just, 100 kilogram, 0.1 kilograms. All right, so we got that. That means, now that I have the mass of water, the only thing in this equation that I have, let's call this equation 1, right? So the only thing I don't have here is the final temperature. And we just go ahead and pretty much solve for that. And it's gonna, take a little bit of algebra, right? So remember, so technically I have the initial temperature of, let me put, initial temperature of this guy here as 300 degrees Celsius, and initial temperature of the water here is 20 degrees Celsius, okay? So if I do that, I have to do then, distribute this. So I have then MC times specific heat of C times T final of C, then minus, then what I have here is 300 times MC specific heat of C, right? And then plus, then M water, C water times final temperature of water, then minus 20 times M water specific heat of water, and that's equals to 0. Okay, that means what I have here is there are now 2 terms with a T final, right? And 2 terms that don't have T final. So I keep those terms with a T final, where I have MC C of the copper times T final, then plus M water specific of water times T final, and move the other 2 to the other side. Okay, so equals to, then I have 300 MC CC plus 20 M water specific of water. All right, then I come back to the left side, and I can then, you can see, right, I can factor out then the T final, which becomes MC specific of C plus M water, specific of water. And on the right side, I just still have 300 mass of copper, specific of copper, plus 20 mass of water, specific of water. And then what I do here is divide by, the quantity in the parentheses. That means MC cup C plus M water cup, specific of water, okay? So if I divide by that, those cancel out, then I have just a temperature final equation, which is going to be 300 times mass of the copper, which is 0.03, times specific of copper, 385, plus then 20, then mass of the water, which end up 0.1, then times specific of water, which is 4190, and that quantity, right, then divided by mass of the copper, 0.03, times specific heat, right, 385, then plus mass of the water, 0.1, times specific of water, 4190. All right, so we end up with basically this final equation. Okay, and you can see, right, we have everything that we need. You calculate, T final equals 28 degrees Celsius. All right, and that's basically our final answer. And we can see, right, we didn't have to worry about any type of phase change because at 28 degrees Celsius, the water is still water, right? And this Q2, which is the energy absorbed by water, only changed the temperature about, about 8 degrees, right? Where the copper pellet, changed the temperature by basically, went from 300 to, 300 to 28. So much more significant change in temperature for the copper pellet. But anyway, so this is, how you would rearrange this type of equations, right? And solve for the final temperature. All right, guys, so that's it for chapter 14. So chapter 15, again, it's a little bit shorter chapter. I posted in terms of which section I will be covering. So make sure you guys, watch this video and the next one when it's posted, and prepare, with basically to practice all the homework problems and, prepare for the final exam.